Here's our first set of problems. And on these, we're going to practice skills that maybe we already have, but we're really going to extend them and start to think about how those skills that we have are applied to new scenarios. So the first one here is not hopefully too different from something that you've thought about and done in first year chemistry. Calculate the number of atoms in a certain number of grams. So as we do that, we need to think about what the relationships that we know are. Well, we're starting with grams. So when we have a value, we start by writing the number, the unit, and paying attention to what element or compound we're talking about. The more carefully we label our work and keep track of our work, the easier it is to work through it. And as we start to get to more complex problems or multi-part problems, then it's really easy to come back to the information that we need. So we know we have grams of carbon and we want to connect that to another value. We'll see throughout all of this unit and all of this year, if you have something that's not in moles, probably that your best bet is to change it to moles. So when I divide by grams, that gets me to moles as long as I use the molar mass from the periodic table. So using our equation sheet for AP or using the periodic table in the textbook or on the wall, we see that there's 12 grams in every 1 mole of carbon, 12.01 to be precise. And that could get us to moles, but it asks for how many atoms. 1 mole of any element, any compound, any item is 6.02 times 10 to the 23rd of those items. So we divide by the molar mass, multiply by Avogadro's number, we get our final answer here. And because it was a small mass, we have less than 10 times 10 to the 23rd, in terms of atoms, but we still have huge number of atoms there. Because this had some place holding zeros at the beginning, those weren't significant. So I just had 1, 2, 3 digits that were significant. I carried that through all of my math, and my final answer has 3 as well. And it's also labeled with its unit as well as the formula. Part B is a lot the same, going the other direction. We're talking about exactly 1 million atoms of uranium. So 1 million's a fairly big number if we're talking about money or some other thing that we're trying to count. But because atoms are so small, we're going to see how small that is even for one of our heavier elements. So atoms, the connection from atoms to anything else is Avogadro's number. We've got it right there. That's how many are in 1 mole. And then for uranium, its molar mass is way bigger than carbon or hydrogen or others. It's in that 207 range. So we divide by this. We need to be really careful that we know how to put scientific notation into our calculator. We multiply up here, and then we get an answer that's got a whole bunch of zeros at the beginning. 0.00000. There should be 15 zeros, and then our answer. This one's a little bit tricky in terms of significant figures. It's at exactly 1 million. So even though that looks like it just has 1 digit, or maybe it looks like it has 7 digits, we treat it as if it has an infinite number of significant figures. Normally, we wouldn't round based upon a molar mass or Avogadro's number because they are known much more precisely than any measured value. But this time, we're kind of in a sticky situation. If you rounded it 3 digits, you probably wouldn't lose any points. But because Avogadro's number and the molar mass are both presented to us with 4 digits, rounding to 4 is a very good bet. Question C of number 1 here is where we get a little bit deeper into the application. We have the skills, we know how they can be used, but where do we need to plug them in this time? So we've got an aluminum sphere that's got a whole bunch of atoms, but we see that it's to the 22nd, so not quite 1 mole's worth. That's a good skill to be able to kind of develop and estimate. If I have less than a mole, then when I get to my grams, it's going to be less than the molar mass. It asks about the radius in centimeters. We have the density here in grams per centimeter cubed. So we start with all the same steps we had before. We've got atoms, we change it to moles. Well, if I want to make a connection between my measured amount of aluminum To how big it is, I'm going to be using its density, which requires grams and cubic centimeters. So that's how I know to use molar mass here. I divide, I get my grams. I've got just under 4 grams of aluminum, which, as I said, makes sense. It's less than a mole. Grams connects to density by the density equation here. D equals M over V. We know the M, we know the D, we don't know what the volume is. So we plug that in. Be very careful or very aware as you're doing this. This is an easy one when you're solving for volume to fall into the trap of just multiplying these numbers or dividing them incorrectly. So make sure we're rearranging and doing that correctly. We get 1.42. And then you wouldn't necessarily need to know the equation for the radius of a sphere off the top of your head for this or any question. But we know our volume. We get 4/3 pi r cubed. That's how we get the relationship with the radius. And that does allow us to know our radius is just over 1/2 of a centimeter. So our sphere as a whole is going to be a little bit more than 1 centimeter in diameter. So taking some simple dimensional analysis, mole calculations, or mole skills, and starting to apply them to kind of that next step is where we go from the simple initial introductory chemistry to starting to think more in terms of how can I solve this in an AP chemistry approach.